Well, today we're dealing with fire protection and prevention. So the whole goal is to keep a fire from ever happening, from ever having a picture like this. But stuff happens, and so you can never just say we're going to prevent fires. You've also got to be ready to deal with the actual fire. So you have to be prepared for everything. Okay, so yes, we're going to be looking at fire extinguishers, properly handling of flammable materials, and such. We'll be looking at the different types of fires. But first of all, looking at the OSHA standards, the construction section, the construction standards, 1926, their portion dealing with fire starts with F, subpart F. So F is easy to remember, F in fire. That's not really how the alphabet works, but this one does on the when you're looking at the different letters that they assign to different sections of the standards. But it basically 1926, 150 through 159. And you'll see these, some headings like things about extinguishing systems further down, a couple of different systems about general and then gaseous agent and such. Now let's go over to the general industry standard, 1910. And in there's actually more sections. Again, any work that's not specifically construction work, everything from flipping burgers at McDonald's to dry cleaning outfit, anything that's not construction falls under the general industry standards. And they have a bunch of appendices, so it's very well developed. There's more sections, but still a lot of the similar sections dealing with extinguishing systems and such. Okay, so yes, part of the standard deals with flammables or combustibles, fire extinguishers, the storage of flammable materials, the fire protection program and equipment, and the different extinguishers and such. Okay, so first of all, in the beginning, fire is a hazard that is both extremely dangerous and highly preventable. Just about every fire, you can say, well, gosh, we sure could have prevented that if we had done just this or that. And that's certainly true with house fires. It's true on many job sites. You've got flammable materials, fuel sources, and you want to keep them away from ignition sources. So fuel sources on a construction site can be combustible building materials and lumber scraps and trash piles and dumpsters full of things like that, including but also on your site, you've got bulk fuel, maybe some flammable paints or solvents, welding gases, maybe fuel for like gasoline or propane or diesel for some of the equipment on the site, and other flammable materials that you might work with, like, oh gosh, there's so many of them, but, paint thinner. Well, that's a paint solvent, basically. So many of these liquid fuels, flammables, have invisible vapors as they evaporate. In fact, when you're dealing with liquid fuels in general, the part that actually burns isn't the liquid. It's the vapor, the stuff that's evaporating off the surface. So some liquids give off enough vapor at room temperature to form flammable mixtures in the air. So it's the employer responsibility to develop and maintain an effective fire protection and prevention program on the job site and through all phases of construction. So your planning as a construction manager means that you are thinking about each phase of the job and what you need to do to prevent fires and to protect your employees and the job. There's been many a job that's literally burned to the ground, and then you're starting all over again, and maybe the company is a bankrupt because of the fire, because they're starting all over too. So prevention is certainly a huge key part of this. Now, so first of all, just thinking about your home, you should look around and think about things around your home that could possibly start fires. What are the heat sources that you might have, like a toaster oven that maybe needs to be cleaned? As we get into the winter time, people bring out portable heaters. And the problem is that maybe a blanket can get flipped over onto that or a pillow or something, and next thing you know, you've got a fire. Or they tip over. Well, the newer versions of the heaters tend to shut off if they tip over. So that's less of a problem, but it's typically the blanket over top of the heater, or just being, or running the heater on a puny extension cord. So frayed extension cords or overcharged extension cords can cause this problem. So electrical hazards are often tied with fire hazards. So that's the home. Whether you have a burner left on while you're cooking in the other room compared to what you're doing at your computer or watching TV or busy with something else. On the job site, we got flammables, we got heat sources. We can have defective tools and equipment that become the heat sources. You got to separate the flammables away from where you're working. For instance, if you're going to do some welding, you shouldn't really be doing that around flammable materials. Sometimes, though, you cannot do that. Maybe you can't move the flammables. Sometimes you have to protect the flammables with fireproof blankets and other techniques like that. So a big part of job safety systems is we set up things like JSAs, job safety analysis processes, where we analyze each of the steps of a job and try to figure out what the hazard issues, what the dangerous issues are at each step along the way. And one big part of that is often fire prevention. And the same thing with work permits. And so work permits, you're not going to see them on a general construction site, but you will see them in the plants. They're required. OSHA requires the petrochemical industry and other high hazard work that's classified and specified as high hazard work by OSHA, that you have a work permit process, that the host company that's running the plant have and enforce a work permit system where nobody can do anything without a work permit. And there's different kinds of work permits, and one of them has to do with is called hot work permit, and that's things that can start fires. It can be just welding or grinding. You create sparks, and so therefore that's a fire hazard, because anything that the sparks could catch to or could ignite, particularly in the plants where they've got gases that can leak at any time. And when those flammable gases meet up in the right concentration with sparks, or a spark, that's all it takes. Okay, so I just bring up this picture about the Roomba because one of my brothers had a Roomba that was running wild around his condominium, his fancy condo way up 15, 20 stories in the air, overlooking Manhattan but in Hoboken, New Jersey, across the river. While they were gone on vacation, I guess this Roomba knocked over a lamp onto the curtains. And when they came back, his wife and he both ran to two separate bathrooms because they needed to pee or something. And as they came out of the bathrooms, they discovered the curtains were on fire. So my brother Chris, he just grabbed the curtains and threw them off the balcony 15, 20 stories up. Yay, I saved our home. Well, the curtains landed on some pine trees down below, started a great big torch that they could feel the heat from. It was a very impressive torch. So he's a biochemist, and he's always making wine, and whatever can't be turned into wine is turned into a still or something. He never throws any alcohol out. He gets it one way or the other. But the point is, he had a garden hose that he could hook up to the sink. Because of that he was able to try to spray water. Well, 15 stories up or whatever, that didn't do too much good. But the trees were eventually kind of winding down when the fire truck arrived. And then he yelled to his wife to shut off the lights, and they hid quietly, and nobody seemed to notice. Nobody reported them anyways. A few days later, there was a newsletter going around for their community from their building saying, be on the lookout, some homeless people started a fire down below. Well, so they blamed it on the homeless. But anyways, the point here being that you think you can plan for every scenario and prevent a fire, you just can't. Stuff will happen. So this was a weird combination where a halogen light, the old halogen lights that didn't have a proper cover, halogen lights, traditionally the 120 volt style, they get so hot that they can ignite things immediately. It's just like putting gasoline on a match to gasoline. They light those curtains quickly. Anyways, so sources of ignition, we have this fire triangle that you really, in order to have a fire, you've got to have all three of these things. Fuel, and you have to have heat to make the fuel ignite, and you have to have oxygen. And if you can remove any one of these three, you can keep the fire from happening, or you can stop the fire from happening in varying degrees of success. I mean, you do better cooling off a wood fire than you do actually trying to smother it, because the coals are so hot, they store this energy, and it takes... meanwhile, other kinds of things like liquid fires, you really can't cool them off very easily. It's easier to smother them to remove the oxygen. And so there's different techniques depending on the fuel, on what kind of fuel you're dealing with. But there's another dynamic that can happen. You can have let's say a train derailment where two cars that have chemicals that react with each other and produce heat with that chemical reaction can have a whole life of their own. And so they have a three-dimensional triangle, as you say, kind of three-dimensional, and so it's got another leg to the triangle, and that's the reaction, the chemical reaction. So if you've got half the chemical reactions in the universe produce heat, and the other half take heat to happen at all, you have to push heat into the chemical reaction. And so it just depends on what they are, but you can easily have two chemicals that react with each other, two things that react with each other, and they change the whole dynamic of that fire. So, fuel is anything that can combine with oxygen and heat to burn. Oxygen is always present in the air, pretty much. Heat is anything that can raise a fuel's temperature to its flash point. So the flash point is the temperature at which a fuel gives off enough gases, enough vapors to burn. So even something like firewood, you've got, I've lit fires at all temperatures. I've tried to light fires at 35 degrees below zero, and it's not easy. You got to heat that wood up. Not easy at all. So it's true even with wood. But anyways, fires that involve the reactive materials, the two chemicals reacting, can be far more hazardous than other kinds of fires. The heat from these fires can lead to violent, uncontrolled chemical reactions and potentially explosive ruptures, particularly of sealed containers. So that's a concept that could be turned into a test question. So I just kind of want to make sure you understand that a little bit. Okay, so here is a NFPA 704 hazard diamond. So, just like a baseball diamond, it's really a square. Nobody wants to call it a baseball square. They call it a baseball diamond. You tip the square up 45 degrees, and now we call it a diamond. And then this thing is divided into 4 little diamonds. And the top box is all about flammability. So it's normally colored in red. You have to have a bit of imagination to see red here. And over on the left-hand side, you see that where the number 2 is at, you see there, that's all about health hazards, things that are toxic, things that can kill you today, though. They have to be very toxic, poisonous. So a health hazard is in blue. And over on the right-hand side, that diamond is in yellow, and that deals with an instability or a stability, reactivity, but it has more to do with the explosive nature of materials and how violent that is. And so each of those 3 diamonds, we have numbers from 0 all the way up to 4, where 4 is the most dangerous category, and 0, there is no hazard. And then that bottom box, that bottom diamond, deals with things that don't fit neatly into either one of those 3 other categories, and that's usually a non-color white or something. Let me click over to the next page because it kind of shows the same thing over here. But before I do that, I want to point out that NFPA stands for the National Fire Protection Association. You see that down at the bottom. And we call this diamond in this system the NFPA 704 system, or NFPA 704 hazard diamond, as you see that down here. Hazard warning diamond would be another part of that, I guess. And so here I've got colors. Notice that up at the top box, red is the color, and the way that we define how flammable something is completely about the flash point. And notice that the most dangerous condition is when the temperature, the flash point, is at or below room temperature. So that means that right around all of us, all the time, it's always flammable. And so you got enough vapors off to this, so that makes those would be more dangerous than something, let's say number one, where you've got to heat it up above 200 degrees before you have to worry about vapors coming off of it. That's less dangerous. So that's, you see how that works. A lower flash point means it's more dangerous. Okay, so this so the minimum temperature, the flash point is a minimum temperature at which a liquid gives off enough vapor within a test vessel, if you want to get technical, in sufficient concentration to form an ignitable mixture with air near the surface of the liquid. My brothers and I learned kind of together, but really one of my brothers figured it out first, how to make a cute little gun out of a closed peg and a half, a closed pin and a half, that could shoot a wooden match, and light it at the same time. So we could shoot lit matches at each other. It was just great fun until the parents discovered it and took away the closed pegs. But, the technology was in our heads, so there's no way we couldn't forget. We knew what we were doing now. Anyways, at one point when no one was around, we had a bucket of gasoline and we were shooting matches into the gasoline, and then we cover it up with a piece of board and snuff it out and shoot again. It was amazing how many times you could shoot a match that was full of flame into a bucket of gasoline, and the match would just go out like as if it was going into a bucket of water. You had to have the right conditions of the evaporative gases coming off of that that liquid in order to ignite. What you're trying to ignite is the gas that's evaporating on the surface, the vapor. And so we were actually more successful when you weren't even trying to get it into the bucket and just shoot barely over top of the bucket through the cloud. But it just goes to show you got to have the right concentration. Now, Murphy's Law says if you thought you could get away with not worrying about such a thing, then that concentration would just magically get to be just right, and then you'd have an explosion or a fire. So we have an old system of classes of flammable and combustible liquids, class 1, 2, and 3 in Roman numerals. And again, the class 1 is the most dangerous condition for a flammable liquid, and that's where we had a flash point basically at or below room temperature, 73 degrees. And the least dangerous was way down there at the bottom. So it's still all about flash point. Now, in modern times, we've replaced this system with a category system instead of classes. It's part of this globally harmonized system where we're trying to make a standardized system across the world. And in doing so, category 1 is still the most dangerous, but they've gotten rid of the word combustible. So liquids are no longer considered combustible. They're either flammable or they're not. What we still reserve the word combustible for in the safety business is dust. Anything powdery, dusty, ground metals, all kinds of things like that. It could be powders, everything from coffee creamer to sawdust and many things that can ignite, and things that types of dust that you would never think would ignite can ignite. It's really quite amazing. But combustible dusts, so dusts are combustible, liquids are flammable, or they're not. Anyway, so I've got maybe way more terms that I should have in here along the way here, but I just want, in the new system, they've got the 4 different categories instead of those 3 classes that we had back here and subclasses that they had here. So let's kind of skip along a little bit. I tried my darndest to find something, but really the best picture is this fuzzy one here, flammable 1, 2, 3, and 4. I was trying to find a table that had Fahrenheit in there. It has Celsius in one column, second column, and the third column has the Fahrenheit. Anyway, it just gives you an idea. Nothing that you have to memorize here. So something that's really important is to understand the lower explosive limit and the upper explosive limit of a flammable gas, a flammable liquid, really. And so what we're really talking about is vapor in here, but still it comes generally from a liquid, depending on what kind of liquid it is, depending on whether it needs to be under pressure or not. But still, just generally speaking, when we're talking about flammable liquids and therefore flammable vapors over time as it evaporates, you need a certain concentration, depending on the substance, depending on the gas, for it to be explosive, for it to ignite in the air, a certain concentration in the air. And we call that minimum concentration for that to be the lower explosive limit, or LEL. However, there's another term, it's just almost the same. It's called the lower flammable limit, LFL. And that means the same thing, so you can see it either way. And then, if you get too much, you can get to a point where there's so much of a concentration of vapor in the air that it can't ignite anymore, and we call that the upper explosive limit, or the upper flammable limit, the UEL or the UFL, either way. Sounds like a football league or an alien spacecraft. Okay, well anyways, so in between that, and so this happens all the time in real life. If you think about an engine, you got to get just the right concentration in the pistons for the gasoline to ignite, for your engine to run, and if you get too much in there, the engine is flooded and you have to wait for that to evaporate out. If you don't get enough, it's not going to ignite either. Well, here's the thing, is it's very hard to measure accurately the lower explosive limit or the upper explosive limit, because these gases have a certain buoyancy level and they can move around in the air, and so they could conceivably have a higher concentration on one side of the room than the other, or they can have a different concentration because they have a certain buoyancy, where you could have maybe too much up at the very top, not enough down at the very bottom of a tank or inside a shop or inside a room. And then somewhere in the middle, you have the right concentration. And so what OSHA says is you can't work anywhere near. You can't work above the upper explosive limit, but you can't work below, just below the lower explosive limit. They want you to work way below the lower explosive limit. And that is what they call, down at the bottom, you see the last bullet, the permissible exposure limit, PEL. So Pell, like a Pell Grant. Eh? Well, not a Pell Grant, but anyways, maybe it'll help you remember it. But the permissible exposure limit is defined as being 1/10 of the lower explosive limit, or 10%, same thing, of the lower explosive limit. So that's where we have to be. So let's say that the particular gas that we're dealing with has a lower explosive limit of 4%, 4% concentration, and that's what's considered a lower explosive limit. Well, that means we have to do 1/10 of that. That means we move the decimal place over 1 decimal place to the left, and we're looking at 0.4%. So from 4%, the permissible exposure limit is 0.4%. So all you're doing is move the decimal place over 1 place to the left. So that's something to keep keep in mind. All of this stuff that we're talking about, the diamond, the NFPA 704 hazard diamond, and this lower explosive limit, upper explosive limit, the permissible explosive limit, exposure limit, for the Pell. All of these things will also come back and be important when we come to our last topic before the first exam, and that is about hazardous communication. So it's also important because this lingo and language matters there too. So it'll come back a second time here in a couple of videos from now. Okay, so we don't work anywhere in the range between the lower explosive limit and the upper explosive limit, and OSHA won't let us work above it either. So we can only work below it, but well below it, at 1/10 of whatever that space between the vertical line on this graph and that edge where the LAL, we have to work 1/10 of that. And so we test that with meters, and that's what we have to work below. Okay, so we don't end up with something like this or such. So yeah, in fires, you have to have an emergency action plan. That means that an emergency action plan is something that describes the actions employees should take to ensure their safety if a fire or some other emergency occurs. And so fire is one of the main emergencies, but there's other ones. So that's something that's important, that every construction company, every job site should have a safety plan, and part of their safety plan must include an emergency action plan. And we'll come back to talk about that later on in the course, but as something to mention. So these are some examples of things that would be in your emergency action plan. What conditions under which an evacuation would be necessary? You have to have a clear chain of command, a person authorized to order an evacuation. And then you have to have evacuation procedures and emergency escape route assignments. And finally, number 5 is the one that I will turn into a testable point. Number 5, you need a designated meeting area outside of the building, outside of the job site area too. So that if you have a fire, an explosion, a disaster, you've got some kind of designated meeting area where everybody's going to meet as they escape, so that you can do roll call to make sure everybody did get out. You got to figure that out, and that's typically true in any situation, really. Now, actually, what is a best practice is to have 2 designated meeting areas opposite directions from each other, because if the wind is blowing a certain way, it could be blowing poisonous fumes or gases or such toward your designated meeting area. So you need another location so everybody knows if the wind's blowing a certain way, you go to the other meeting area instead. The other part, the main reason for that designated meeting area is number 9, which is another testable point. You need procedures in your emergency action plan for accounting for workers after the evacuation is complete. So you shouldn't just be running to the house and watch it on TV. Somebody might have to risk their lives to go in to try to save you, and you're watching it from the house. That's not right. So that's the goal here, is to make sure everybody got out so that we're not looking for people that don't need to be rescued. Okay, so even in buildings like our classroom, the buildings our classroom is in, just to get the final building permit to build the structure, you've got to have an escape plan that is all planned out. You've got to assign how many people can even officially be in any particular room. So our regular classroom for this class, in room 116, has a rating of 40 people. So literally the fire marshal, if they were to come and find you had 50 people in there, they could shut the building down and issue you a citation and fines. So that can happen. You got to have a fire extinguishers at the top of every stairway. You have to have a certain number of fire extinguishers throughout the building, depending on a certain amount per square feet and such too. Okay, so the site layout of your job site. You should be organizing your job site so that flammables are kept away from habitable areas like the lunch tent, the lunch room, or the office. So, and this is a bad situation here where this little office, portable office unit here, the guy's got to come out that door and fight past that fire just to get away from it. And that's not a good practice. So going down hallways in buildings and even outside, in as far as paths for vehicles to escape and such, you need to keep pathways clear so that in an emergency, an escape is not a hard thing to do. And so in here, that pallet and that mop should not be on the right-hand side of that line. They should be over on the other side. That line is meant to mean that everything should be kept clear along that path. One day I was teaching a class, and I was in a very big room where we had 88 seats, and there's about 20 of us in there. But I was joking about how, well, we got these big double doors down here in the front. We can always escape out there very easily. And somebody said, back when you were kind of allowed to smoke, or they tolerated it, people were out here and they would notice and look at those sandbags that somebody at the campus, the facility services, had put in there to try to keep the water that splashes off the roof from hitting. When it hits the concrete, some of that water would drive underneath the door and get the carpet wet. And so this was their solution to that. So I looked over here. We counted these bags, and I figured there's 17 bags. There's about 1,000 pounds here, especially when the sand is wet from the rain and stuff. It took quite a few of us to push these doors open. So I moved the bags out of the way, and then I took pictures first, and then we moved the bags away, and we said, you can't do this and everything. And lo and behold, about a week later, they were back again. They had stacked them back up there again. So this time I took a knife and sliced each one of those bags open. So they were going to at least have to make new sandbags. But you just cannot block doorways like this or with furniture or anything like that. It's not allowed. And that would be a serious infraction. The fire marshal could really shut this place down. Okay, so there's common sense in fire prevention. You use fire-resistant tarps and covers if you have to protect. You use temporary heaters very carefully. You should have no more than 1 day's supply of flammable material inside the building. So that's one rule. The OSHA somewhere else defines that as no more than 5 gallons of gasoline, or no more than 10 pounds of propane. So basically, when they tell you a building, they're not talking about your bedroom. That's not a right place to have any of that stuff. But they're talking about inside of a warehouse or inside of a shop. So these flammable liquids should be kept stored somewhere else, not in your shop. Anyways, so let's see. So storage of materials. So an official gas can should not be made of plastic. Now I know I've got some around my house, especially I've tucked some in my attic ready to pull out whenever there's a hurricane coming. So I'm ready to get some fuel for my generator. But on your job site, you shouldn't be playing around with plastic gas cans. You should have what we call a safety can. It's made of metal. You see it on the left-hand side of this page here. A spring-loaded lid. And that spring-loaded lid has several different roles. And then if you're storing a bunch of fuel, it should be stored in a proper safety cabinet. So these cans or other kinds of fuel, maybe propane bottles, should be, or spray cans of paint even, and maybe little plumbing torches and stuff, should all be stored in a safety cabinet. Both the safety can and the safety cabinet must be approved containers. That means that they're UL listed. UL stands for United Laboratories, so it's United Laboratories listed. That's an official certification about the safety of that container or that cabinet, and other things that United Laboratories rates and specifies. By the way, that safety cabinet is supposed to be grounded, and they don't call it that. They say bonded to a known ground. Okay, not this. You shouldn't have all this stuff next to where you sleep or eat or rest or whatever. You got to keep this stuff stored elsewhere in proper containers, cabinets, away from everybody. So, safety cabinet, important for proper storage of flammables and combustibles. And that's a metal cabinet, by the way. It's not a plastic container or cabinet. So, the safety can, that lid has many built-in safety features, such as vapor control. Well, that's the spring-loaded lid there with a handle on it. Flame arrestor, well, that's the lid. And a pressure relief valve, well, that's that spring-loaded lid. So it's all about the same thing. But the idea is that if there's too much pressure, it'll bleed off. But otherwise, it's keeping the vapor from evaporating off quickly. But here's the reason it's made of metal. It has to be made of metal. It's because you're supposed to, as you pour gasoline or some other fuel from one container to another, the two containers are supposed to be bonded to each other with a electrical wire. You can't do that with a plastic container. You can't do it, so you cannot control the static charges. That's why these containers have to be made of metal. So a safety can also means an approved container, as we were talking about, not more than 5 gallons. So that's also a limit. This safety can is going to be no more than 5 gallons. So finally, we're getting to the other area here, and that's about fire protection and prevention. That's the fire extinguishers themselves. Now, the first thing is this picture shows a fire extinguisher that is actually discharged. You see the pressure gauge is below where it's supposed to be, in the green in the center of that gauge. It's also tied closed, which is probably because it's already been spent. So either way, this is a fire extinguisher that you cannot count on. You shouldn't need wire clippers to cut the thing in order to use it. Well, this thing's probably spent anyway, so it wouldn't matter. So fire extinguishers should be inspected regularly. You pick them up to make sure they weigh the right amount, check the pressure, but they actually have to be officially inspected by a qualified person once per year. So the tags that go on these things will have the date punched out. This is a pretty old date here, but anyways, the date would be punched out if it was actually an active fire extinguisher tag, and the month marked. That year is not when it expires. You see where it says on the tag underneath 1999, 2000, 2001, it says void 1 year from month punched in the system here. So they punch both, basically, is ideally what they do, but sometimes I see them mark one and punch the other. They punch the month for sure. With a paper punch, usually a diamond-shaped paper puncher is what I've seen. But anyways, I digress. So that's the thing to remember, so you don't get laughed at or made into a fool at some point. When you check the tag to see what the date is, the date isn't the date that it expires. It's the date that it was serviced. And when that date is more than 1 year from the current date, then you know it's got to, that you know it's expired. Okay, so you never fight a fire if the fire is large and spreading beyond the immediate area. You've got to make a judgment call. But here's the thing: these extinguishers just don't last that long. You get about a second or two per pound, and so you better aim wisely at the base of the fire before you ever pull that trigger, and then be prepared to move that fire extinguisher because you may not aim quite right. You're shooting from the hip. It's not like you got a gun sights on this thing. So yeah, and so you gotta, if you're in a confined area like a house, like a shop, the fire is removing oxygen from the air, it's putting smoke into the air. All these things could mean you could be passing out soon. So you really can't, the reason for using a firefighter is if you can snuff it out early in the very beginning. That can make all the difference. But once that fire is roaring, you're not going to put it out with a fire extinguisher. It's too late. So the classes of fires, that's an important thing that can be turned into in several ways into test questions. So class A, B, C, and D are the normal fire extinguishers on a construction site. I threw in K down at the bottom for restaurants and cooking media. It might come up in your career somewhere along the way. But so class A, that's ordinary combustibles. That's things like wood, lumber, cloth, paper, things that you might have in a dumpster. Class B fires involve flammable liquids such as gasoline, oil, oil-based paint, anything flammable in liquid form, and somewhat gaseous form too, because they're usually involved together. And then Class C fires involve energized electrical equipment. So, when we talk about an electrical fire, we're not saying that the electricity is on fire. Electricity is the energy that makes other things burn. So it's the heat. It's not the it's not the fuel. But here's the thing: if you've got a garden hose or even the fire hydrant hose from the firefighters use, you can put out Class A fires all the time with that. Class B, you can't use water because the flammable liquid will bounce all over the place. Instead of having one big fire, you'll have 50 individual fires all over the place, spreading worse and maybe bouncing back at you, and maybe you're on fire. So you can't put water on flammable liquid. A Class B fire, you can't use water. Class C, you can't use water either because it could conduct right back through the stream of your garden hose or your fire hydrant hose. So Class C fires, you don't use water either. So look at that. Okay, so there are special fire extinguishers for each one of these fires, although the most common fire extinguisher for people to have, the one that you might have around handy, is going to likely be, and the one that you probably should have on your site, would be rated for all three, for Class A, B, and C fires. And that way it's non-conductive, so it'll work on Class C fires. It'll work on one that you need the fire extinguisher that'll work also on flammable liquids and ordinary combustibles. So that's the Class A, B, C fire extinguisher. There's one other class I hadn't talked about, and that's the Class D fire, and that's ones involving combustible metals, combustible metal dust. It's not a chunk of aluminum that burns. It's not a chunk of iron that burns. But if you get iron filings or aluminum filings, they make great bombs. They make great fireworks. So metals, the most common metals that we use to burn on purpose would be magnesium, titanium, potassium, or sodium. And yes, sodium and potassium are classified as metalloids. They are metals. So the Class D fire extinguishers are yellow. The tanks are yellow, whereas the Class A, B, C fire extinguishers tend to be red. The Class D in yellow, and then they've got a label on there with a yellow star in there with the D in the center of the star. And there's a pasty material that comes out of a Class D fire extinguisher, where generally the Class A, B, C fire extinguishers that are rated for all three are mostly dry chemical, mostly baking soda, or something of that nature. Not baking powder, that's got flour in it, which would be flammable. So in your kitchen, if you've got a little box of baking soda, that is a fire extinguishing material, but not baking powder. That will burn, or to some degree it will burn. So yes, in theory, we have the triangle with the A in the middle and the square with a B for Class B fires. We have a circle with a C for the Class C fires, and then the star with the D. So there are shapes out there. The one that you need to remember for a test question will be about the yellow star with the D in it. That's for combustible metals. Oh yeah, and the K is a hexagon. Okay, not shown. Anyways, but if you had one of these symbols and you had a red slash through any of these symbols, that means you can't use it on that kind of fire. So that's the other thing. If you've got a slash through it, that means you're not allowed to use it, or you shouldn't use it. So that happens mostly with things like water on a flammable liquid fire or a electrical fire, that sort of thing. But there's other cases here, so we'll look at that a little bit. Yes, they have special colors for each of these classes of fires too, and so I'm not making you memorize that either. But in general, the one that you need to know is the yellow, for the yellow star, like you see there. Okay, so they do have a code system for Class A and B fires, a rating system that from 1 to 40 for Class A, it tells you how good it is, that extinguisher is at fighting that class of fire. So 40 would be better than 1, so the higher the number, the better it is. Class B has a rating system also from 1 to 640, which is crazy. Why couldn't they just make them the same? But I've never seen a Class A fire extinguisher that was ever rated at 40, or a Class B fire extinguisher that was anywhere near 640 either. So the numbers are much smaller than that. Class C and D do not have a numerical rating. So let me see here. There's a bunch of different things to look at, but I think at this point, what the key things, I'm trying to skip along in the interest of time, that looking at some sample fire extinguisher labels. So the first one here on the left is dry chemical, and its rating here, I put the big numbers up top. It's written on the side of the label, but I put them in large numbers up top on the title. 3A, 40B, and C. So this dry chemical is good for class A, B, and C fires, but you can see it's rated pretty well for B and maybe somewhat okay for A. But look at the halon system here. Halon tends to snuff people out, by the way. It's rated for A, B, and C, but not very well for either one. Halon or Halotron is a brand name of a system that is often not used as a fire extinguisher that you would put out a fire with. It's used to arm a whole museum after you're certain everybody is out of the fire, out of the zone where this thing is going to be armed. So it's kind of a part of a security system. And then what the trouble is, it snuffs out people too. And so it's dangerous that way because it removes oxygen from the air. Okay, look at these two fire extinguishers. The one on the left is carbon dioxide, or CO2. And you see it's got a rating of 5 for B, and it's rated for C also. So it's only good for B and C. It's not rated for A. Now actually it's not particularly dangerous for class A fires, but it's not effective on them. And because carbon dioxide doesn't hang around as a gas, so it's good at snuffing out a liquid fire. But it doesn't hang around long enough to do anything in more than just a momentary removal of the flame for a class A fire. So if you've got a building burning, CO2 is not a wise thing to use, so you don't use it for that. But it's not going to, blow anything up or cause more damage. It's just not going to help. It can help with a liquid fire, but not with a paper and wood fire, basically. It's not good for A. Look at the foam here, though. It's good, rated for 1A and 20B, so it's good for both. It's mostly used on liquid fires, but if there is some ordinary combustibles in a Class A, it's okay. But what you cannot use, you see it's got a red line on the label flashing through the electrical equipment, because foam is just like water in that it's going to conduct back through to you. So you can't use a foam fire extinguisher on an electrical fire. So that's an important thing. Both of these things could be turned into test questions near you. I should have a pair of red asterisks next to each one of these things. You'll see it in a few test questions in the quizzes for this chapter, or this topic. And here's what the label on a Class D fire extinguisher looks like. It'll have that D inside a yellow star. And then the whole tank will be red, yellow, so I should have probably put the background yellow on here. That might have helped. There are some old museum fire extinguishers that you can find that are just basically a tank full of water, and in fact some of them you're just pumping it because it didn't have pressure, and they would put out ordinary Class A fires that way. So this is basically stating what we just saw on this page back here, right here in the text. Your carbon dioxide models have liquid CO2 and of course it's pushing it out as a gas, and they're used for Class B and A. And I say also A I put in there, but really it is not prohibited, but it's not going to help so much. But there's no residue, so it's nice and clean. So as you can put out a flammable liquid fire, CO2 is the best. Foam models coat the surface of the burning liquid, but again they conduct. So that's the problem with them. Dry chemical models leave messy white powder, looks like a cocaine party. Ammonium phosphate is also dry chemical. Not good for grease fires apparently. Sodium bicarbonate, that's baking soda. Potassium bicarbonate, just something related, kind of like baking soda. Potassium chloride, or even regular table salt, can be used to put out Class B and C fires. And they can be used on A fires also. And then the halon systems, they smother out people too, is a problem. So we have this system called PASS. Let me kind of bring it up on another page here. I think it's better. PASS. The abbreviations, the P stands for you pull the pin on the fire extinguisher. It's basically the technique of how you use a fire extinguisher. A for aiming the nozzle, not just anywhere, but at the base of the flames, unlike the picture here. And then this first S stands for squeezing the trigger. And then you're not going to necessarily get perfect aim right away, so you got to be ready to use the second S, where you sweep the extinguisher from side to side at the base. Covering as quickly as you can, because you're going to run out of fire extinguisher very quickly. They last seconds, not minutes. So sometimes you pull the trigger for a moment and then stop and then pull again, so you can maybe conserve your powder. Anyways, so you can't hide a fire extinguisher behind a bunch of junk, so you have to leave it in the open. So you need to think about that in every building that you're ever managing or part of, construction site, that the extinguishers need to be kept out where they can be accessible, not hidden behind stuff. Okay, as I'm skipping along here, coming toward the end here, these are some of the things I had mentioned about fire extinguisher rules in buildings. You need a fire extinguisher every 3,000 square feet in a building. In protected areas, the travel distance to extinguisher you shouldn't have to run any more than 100 feet to get to an extinguisher. So basically, every 3,000 square feet, and also a extinguisher should always be within 100 feet of you in a building. So you try to satisfy both of those conditions. And you should have a minimum of one extinguisher per floor. And of course, more if you've got huge square footage here. And then at the stairways, you have to have an extinguisher at the top of every stairway. So by the time you satisfy that, you end up with usually more than one every 3,000 square feet because of that, at least. And then if you're around flammable liquids or flammable gases, you have to have a fire extinguisher that is rated at least for 10B. So it has to be up at that number 10 level on the rating system for how good it is at fighting a Class B fire. So these are things that you should know in as far as the running a construction project, really, when it comes down to it. And it also comes down to, that's the kind of stuff that would be specified in the specifications of a building, about how many fire extinguishers you need for a building. They should be written on a fire plan of some sort for the commercial buildings and above. It doesn't get mentioned on residential buildings, or it would in an apartment complex, but because that's really a commercial construction code. But on residential construction codes, when you're talking about the IRC, the International Residential Code, that wouldn't get specified, would not be. Okay, well, beyond that, some of this is a bit of a repeat and about the idea of the flammable liquids and stuff, and bonding required as you're fueling from a container like this to your fuel can. That means an electrical wire clip to both containers, so they're electrically connected. Or, like with your car, when you fuel up your car, you've got a metal receptacle in the gas tank housing when you open up the gas tank, and you got a metal hose so that they electrically connect with each other. So they are electrically connected when you start fueling to reduce the static charge hazard. Static charge is a little bit less of an issue, or maybe significantly less of an issue in Louisiana most of the time, because we have such humidity. So it's more of an issue in Louisiana in the wintertime. But even so, it's nothing like what we had where I grew up in Western Canada, where we were so dry that you could hear the static charge across the room, something that you never hear around here. Okay, beyond that, just mentioned the storage of natural gas, the storage of propane. You've got to make sure that you have gone to great efforts to separate them with distance, and make sure everything's grounded so you can reduce the explosive hazard there too. So at the end of some of these presentations, I've kind of made a bit of a summary, but it's kind of the same thing that would be in more detail in the study guide anyway. So it's there, if you want to look at it, is here, but it's also important that you kind of review this in the study guide, because these are things that are important. Maybe the red writing here is useful for pointing out the most important stuff in here, so you may want to look at it. So 6 pages, how do you like that for a title page? Eh? Well, that's my niece many years ago. She's not actually in the fire, she's behind it, so it just kind of looks like she's in there. Okay, well, I think that's enough about fire protection and prevention.